Plenary 2. My name is Richard Marsh. I'm a professor at Cardiff University and I never need a microphone. In this session we'll be looking at CO2 transport and we have three speakers. That's James from WSP, Ben from BP and Jackie from ROSEN. And hopefully we'll understand some of the significance and the challenges in transport. And one of the things I'm looking forward to in this session is that whenever you quite often go to a presentation on how we move CO2 around, or how we move energy around, there's always lots of arrows, isn't there? There's always, it's going to go big. These are the people who are going to explain to us what is going on inside the arrows. That's what we need to bear in mind. So without further ado, I will hand over to James.
That was quite onerous, actually, Richard. Thank you. Good afternoon. My name is James Watt. I'm technical director at WSP, which is the largest engineering company no one has ever heard of. I won't give you the business spiel, but just look us up. It's WSP.com. I have to do two disclaimers because I'm doing CCS. WSP is currently the government's advisor, designated advisor on the CCS competitions. I do not sit inside that project. I'm not allowed to touch that project because I help design Net Zero Teesside, the pipeline network anyway, and some HyNet stuff. And I have another disclaimer. If anyone asks me about hydrogen question, we're also the government's advisor on hydrogen. I do sit in that team, so please don't ask me about LCHS, LCHA or anything hydrogen-wise. My head is already on the verge of exploding. I come here for a rest. Two numbers, 53 and 2006. This is where it gets a bit interactive. Does anyone know what those numbers mean, particularly in terms of transport of carbon dioxide? Nope. Simple answer is, last time we were in this building at the UKCCSRC thing, a couple of PhD students were talking about how new CO2 pipelines are. 53 is the age of the Canyon Reef pipeline system in the United States, which is one of the large CO2 pipelines. It was commissioned 4 days before my birthday. So it is 53, like I am. I can assure you at 53 every morning there's nothing new about me. And as my body reminds me every morning as well. 2006, I'll answer in a second. Canyon Reef. I am getting old, so the glasses have to come on. So it shifts 5.2 million tonnes per year over 53 years. Volume-wise, do the maths. It does actually carry a dirty CO2, so it's 85% plus historically. It's 270 million scuffs per day. October 1972 commission. 225 kilometres. It's dense phase, supercritical. And there are notable others. Cortez, 808 kilometres, 19.3 million tonnes. Sheep Mountain, 660, 9.5. Bravo, 350, 7.3. Weyburn, 328 and 5 million tonnes. All of these pipeline systems are bigger than the ones that are proposed in the UK at the moment. So bear that in mind. These things have been built in the 80s. I think the large recently there's been more pipelines talked about in the 2000s, but most of those are 1980s and 1990s delivery. We've been building CO2 pipelines in dense phase, supercritical and gas for a very, very long time. Not a lot of them compared to natural gas and oil and gas, but we have been doing it for a very long time. Not new. 2006, clusters. I am, without doubt, a clusters and infrastructure nerd. I have, as I have told John Gibbons before, a A00 map in my study, which is just over 2 meters tall, 1 meter wide, and it's a map of the UK. And from 2006, when I started modelling clusters, it has every industrial emitter in the UK marked on it with appropriate CO2 pipelines and clustering pipelines in this thing called Penn. Not AI. It is, one of them. It is slowly being translated into Google Earth in those dark nights when I can't sleep. But clusters is a thing. But the first one in 2006 is when it came to fore, when we started thinking in terms of clustering. Even before source to sand, A to B solutions for CO2 pipelines, IEA greenhouse gas R&D program asked the question, how would you do it if you collected them in a collective system? We came up with some weird ideas. Small emitters you could run at 7 bar with a roots blower into a bigger system and then step up the compression and go and go and go and treat it that way. You could do it regionally. And you came up with this concept of actually connecting everything together, and clusters were born. I was in the room with some of the professors here and Ron Oxborough and Jeff Chapman from CCSA when we came up with the terms hub, node, spoke, anchor for describing clusters. But at the very last minute of that project, IEA turned around and said, actually, could you do a worked example? That map was originally drawn on an OS map that I got from a predecessor of Go Outdoors with the good old permanent marker that was then scanned and overlaid with some lines because the permanent marker didn't work. But if you look at the Google Earth model below, that's HiNet. So the history of when we talk about clusters being new and transport solutions being new, they're not. They've been thought of an awful lot in the time that we've been going. That very rapidly led to a cluster developed in Yorkshire. And I quote, there was a guy at E.ON who turned around and said, why did you do it in the Northwest? Because there's nothing interesting in Cheshire. You should do it in Yorkshire. I think at that point he earned a season ticket to the cricket club for bad-mouthing Lancashire and Cheshire. But it meant to Yorkshire, then Humber, Scotland, Teesside, Tyneside, and it did a whole raft of them. Other people did them as well. You know, famously, I always joke with the academics that look at infrastructure. My favourite infrastructure project was the one that said, yeah, we can cluster the whole of the UK and ran a pipeline through Birmingham and didn't notice. We've got offices in Birmingham. It could do with an improvement, but I don't think running a 36-inch pipeline down the Queensway would do anyone any favours. But it's not new. It's something we've been talking about for a very long time. But how do we get from there to here? One of the key things it's always worth pointing out is the Teesside Collective. It's mentioned in the slides. It comes with an obligatory warning. Do not Google Teesside Collective and click on the link that says teessidecollective.co.uk. It published the documents. The TDCA, the local authority, published the documents in 2015, 16, 17. They were all there, the entire study, the precursors to the business models, everything. Then they stopped paying the bill for the website. In 2022, in WSP land, I clicked the link because I wanted the documents. 30 seconds later, my phone went off and it was IT saying, what the hell are you looking at? As I was trying to scrub the image of the escort agency that now owns the website from my eyes. Kudos to the IT response team, but don't Google. If you want the documents from Teesside Collective, drop me an email. I have them without the escort agency's number written on. But they're not new. And this is where we are now. We have Acorn, Net Zero Teesside, HiNet, Highline South, the one in South Wales. We have Viking. We had Silent Cluster, although that seems to have been paused. And we've got an interlinking where clusters are becoming interlinked. HiNet and Peak, Teesside, East Coast, as it travels down to Humber. We've moved forward with feeds for gas pipelines. We had White Rose, we had Longannet, which was one of mine. The Masdar project in UAE was one of mine. That's been developed and gone. We've seen Kings North. We've had offshore stuff being looked at. Everything has been building knowledge. In the meantime, we weren't allowed to use clusters in the competitions, but every time we designed a pipeline, it contributed to how we move forward. Regulations have changed. The piping standard changed in response to CO2, so BSPD 8010 changed. We now have API 1192, which has been published this year for the first time, representing the coming together of the American industry's knowledge, which is vital for our development. We've had EI guidance. We have finally this year had pipeline safety regulations changed to include carbon dioxide. The next step will be COMA, and having carbon dioxide enabled for NPT will become reliant on COMA, and the regulations are changing there. That request to change PSR first came into the speak around 2008, 2009. It takes too long. And hot topics have been clusters or not clusters, safety, dispersion, corrosion, integrity, the equations of state. and composition. If you're an academic working on equations of state, you have my kudos. I've seen the maths, it's horrible, but you need to get that into industry. You need to find a way to make it deployable for us. And then you now have shipping, road and rail and non-pipeline transport, which UKCCSRC has taken a role on. We've had the conference this year, which I didn't make, sorry guys. But it's not a new concept. There is a road terminal for CO2 on Teesside. It's just, its end customer is Coca-Cola. You know, we know we can ship it by road. We know the safety implications. How's industry and academia met, or how's academia-led projects contributed? From the transport side of things, CASN, which is a little-known project that looked at full chain storage to emitter with Heriot Watt in Edinburgh, which was excellent. Pipetrans, which was about the piping issues, mechanicals, dispersion. Mattrans, which is about materials transmission for transport pipelines. Cooltrans, about cooling and dispersion. We've had ZEP, we've had discussions around water solubility, the US, flow metering, knowledge transfer from CCS projects, the international knowledge cooperation, all of it facilitated by academics in this room, all of it bringing research projects forward through the centre and outside of the centre that has contributed to building a good knowledge base. Water solubility is one of my favourite ones because if you go to the published textbook on CO2 pipelines by Mahipur, he gives you a number in pounds per scuff of water content. I challenge all of you to go and check that text if you can find it, because he got his unit conversions wrong. For the first 2 years, he's talking about water solubility and CO2. Everyone was saying the water level's 10 times higher than it should be. The problem with Americans and meters cubed and scuffs. So it's contributed. Everything we've done here has brought us to the next stage. What's changed though? Research, and I'm not going to apologise for this slide because we were told to use Copilot in all our presentation slides, and I was struggling with this one. I just said, Copilot, go do that, and it did this. I was like, all that money. Research, gas dispersion, compositions and corrosion, metering, critical issues. Fiscal metering is a commercial issue, not a technical issue. You have to get it right. There's been lots of research on that. System-wide thinking has come to the fore. We're now thinking about clusters in the right way and how we interact with the electricity systems, and it's become more complex. Knowledge building and capability and capacity increases. It's always great to run into people that have come through the centre or master's programs in industry. And how many of the PhDs that have turned into professors or senior lecturers, that is all part of that capability and capacity building, which the centre is really important for. And the funding competitions have finally gone the right way and gone with clusters rather than source to sand models. What else changed? We did. The challenge has changed. It's become even more complex and more, and I would argue more costly than it was 20 years ago. How do we decarbonise with competing issues around electrification, general decarbonisation, reformulating, refuelling, renewable versus combustion-based energy is also changing, which means profiles on our CO2 pipelines become more difficult, more up and down, not less steady. Industry has become more knowledgeable, but less knowledgeable at the same time. And my challenge is, just because you haven't heard that CO2 corrosion has been studied before doesn't mean it hasn't happened. There was a massive, as you can imagine with Canyon Reef in 1972, there was a massive program of CO2 corrosion tests that are in the 1960s. But we're repeating them now rather than relying on something that was done before. The biggest test program for CO2 and its impact on water is actually from the AGR program in the UK, where at Berkeley, at the nuclear laboratories in Birchwood, they have CO2 samples that have been immersed in steel that has been immersed in CO2 for 40 years, so they can test the behaviour of nuclear reactors. So it's about drawing all of that knowledge in. And yeah, the surprise last time I was here was CO2 pipelines are new. They're 53 years old, nothing new, nothing at all. Our tools are getting smarter. GPROMS, GCCS was a program that came out of involvement through this organisation and CCSA. You've got Continuum and GoldSet, which most people in this room won't know, but they're mapping software. You have InfraCCS, SimCCS, OL sites that are all GIS-based infrastructure model tools that we never had. That 2006 model is the most insane, one of the most insane Excel spreadsheets that I've ever known, not helped by the guy who programmed the spreadsheet was Dutch, and the instructions in the model are Dutch. So I think there's only 2 people in the world who know how to use it, me and a Japanese academic. But RunPilot is another thing that people won't widely know in the industry, but it's a University of Sheffield spin-out from Solomon Brown and his group here at the university that does infrastructure mapping and can do all the dynamic testing of what project comes on, what project comes off, look for all the economic assessments, like all those other bits of software. It's really cool, but it came out of this university. So it's something we need to recognise. Industrial decarbonisation plans, slowly we moved on clusters. I'm not going to go off on a rant on the decarbonisation plans, but what did they do other than generate paper, would be my question. And we got a little bit more risk adverse. We became a little bit more policy led, and sometimes we became a little bit convinced that it couldn't be done and there was more to do. And I'd rather take a more text and engineering attitude and just get on and do the damn thing. The other thing that changed, this map I always put up, these are the UK emitters from 2 years ago. About 1,300 of them all make the national air inventory. I think 11 of them are in CCS clusters. So what do you do about the other 1,100 or so? We need to think the next step of CCS clusters and decarbonisation. And also over that last 20 years, the number of those emitters that are no longer here as decarbonisation has led to closure, or the stress that's being put on our chemicals industry, which is a good thing from a decarbonisation point of view, but not a good thing from a socio-economic point of view. CCS enables us to keep those industries here by making them cleaner, and has a role to play. We also got smarter. I'm of the generation where I've done drawing boards and maps and Google Earth, and now we have tools like this is GoldSet that we automatically use AI to generate route maps and stress test scenarios. AI being deployed, next generation of clusters, and the technology is ready for it. It's a case of whether we are. And going really quickly through this. So what's next? Compositions. What will projects accept? What impact do we have on mixtures? What do we have in terms of empirical data that supports that? How does that impact corrosion integrity questions? Dense phase versus gas. I am a proponent of dense phase pipelines. I'm not going to hide away from that. I think it's far more efficient to do it in dense phase. I understand why projects haven't gone that way. You can do it in gas, but can we ever get to the pace where we can do dense phase pipelines on land? Again, we've kind of forgotten that we already do dense phase pipelines on land. I live on Teesside. In between Scotland, Teesside and the Wirral is a dense phase ethylene liquid pipeline, which is probably the most dangerous pipeline in the UK. But we've done it for that and it's not had a problem, so why can't we do it for something else? Dispersion results. I need to go to Spade Adam just to watch them rather than watch the videos. The amount of work that's been doing on dispersion and how we manage that and how do we model it and how do we get comfortable with the right mathematical model has become really important. But there's still a way to go. A little bit more focus on dense phase in the future, potentially. Cluster and pipeline dynamics. I could harp on about this particular one for hours. When we've been talking about clusters over the years, the thing that's never really been sought or looked at much has been how do clusters react to the emitters and all the different load profiles. This is kind of a hobby project of mine, so you see some of the outputs of the graph. Steady state CCS pipelines are going to be difficult in the future because industry emitters are lower volumes and power is more likely to be peaking, so you have flexibility in the pipelines. The maximum economy out of a pipeline is when that a pipeline is running at capacity all the time, not running at half load, in the expectation that somewhere at 6 o'clock in the morning a power station comes on and its CCS plant runs. So there's some challenges to come with the dynamics. And dynamics isn't just big networks and how they operate, it's how they develop over time. One of the things the Teesside cluster did for the first time in 2015 was designed a network for what it might look like in 20, 30 years and then pared it down to what it should look like now. That's how we should be designing infrastructure to make sure that we're not destroying opportunities for the future. We also have non-pipeline transport. As usual, our Scandinavian colleagues, slightly one step ahead of us, they've got shipping. We've been shipping CO2 across the Baltic and the North Sea for a long time because PepsiCo, Schweppes, the breweries all have their carbon dioxide from industrial processes. A lot of it used to be generated on Teesside and it used to go out on ship. So we know it can be done. It's the interface with the pipeline system. We then have road and rail that integrate. How do we do that? How do we justify road transport? How do we justify and do rail transport? How do we manage the carbon dioxide if it's stuck in rail tankers that are stuck on the sidings for 2 days? All of these things. How do you manage the hazard of moving hazardous chemicals by train and by road? All of these things are questions that we can answer when the projects come up to the fore, or can be future points of discussion. One of the things we learned on one of the study projects was actually having an integrated ship solution with a static network gave you a buffer storage, which was really important to deal with flexibility and gave you so many different options and improved the numbers quite significantly. And lastly, the biggest challenges, and this always spins people, particularly at work, on their heads. I'll start at the bottom. How do we go faster? How do we deploy clusters quicker so they enable emitters to decarbonise quicker than they currently are? How do that enables those emitters to be more economic or have more secure futures rather than the limbo that is waiting around for everything now? Space. How do we use it for all of the competing issues around infrastructure is not well understood and it's not well discussed. How do we run CCS projects and pipelines and infrastructure? How do we do that against hydrogen? How do we do that with the existing gas networks, with the power systems that are coming in place? Most people don't realise if you put a pylon through a piece of countryside that can extract infrastructure, you can't run the pipeline there. You can't get close to the pylon because the induced currents that appear in the pipeline. So you are sterilising a piece of land. So we have to match the infrastructure needs now and in the future. Add to that water and add to that people. We are not unique in this, but a significant number of our clusters are bound by housing because we have a very Victorian approach. There's industry, we'll build houses near the industry so people can walk to work. They got it right back then, but the housing and the population centres grow outwards and that narrows our infrastructure issues or possibilities. Knowledge transfer, how do you get the design, construction, operations of projects and the export of that learning into the academic setting? How do you then use it to cross-train other companies? Because if you ask, I'm sure if you went and asked a certain company that works with an amine capture facility, can you use your knowledge to train 3 of your rivals so we can have a wide pool? They'll say no. That leads to a churn of people, but how do we export that learning from the projects? The knowledge transfer information from the original competitions, competition 1 and 2, were lost, a lost opportunity because everyone was a little bit, I'm going to hide behind my commercial arrangements, I don't really want to talk about learning. We should. We've invested a lot of money in it. We should make sure as the nation, the taxpayers funding it, the knowledge should transfer out, or we should allow academics in to mine that information to then sanitize it and bring it out. How do you import knowledge into the next generation of engineers? I will quite happily talk for hours and hours and hours and teach people how to do clusters, and I've been doing that at Edinburgh for 17 years. They give me a class of master's students for 3 hours on a Friday afternoon. Then it's just a challenge about their attention span, their need for coffee, and my need as a middle-aged man to use the bathroom. And we have to work smarter, and you have the industry, academia, sector engagement has to be better. I miss occasionally these sessions, but always industry needs to be present and academia needs to be present in the industry ones. It's not a one-sided engagement. The last one, and is I think potentially the biggest challenge, and we're seeing it more in hydrogen, we'll see it in CCS as soon as you start stretching beyond the clusters, or as the politics become involved and the people become more engaged. Our landscape in the UK is becoming hugely complicated with projects and people and roads and HS2 has shown that. CO2 pipelines have shown that. Hydrogen pipeline suggestions have seen that. DCOs are flying in left, right, and centre. Those all need to be coordinated so you can manage the message and make sure the public goes with you. And that engagement of stakeholders and on individual projects and themes has to be done in a way that doesn't destroy the opportunities for other projects to come forward. And we have to share that knowledge and raise the education level of the people we're talking to. So it's on us as industry and you as academics as well to find a way to explain CCS to the public that makes them understand and not be scared of it. Because like everything, the things that make the news are the bad things. What we want to say is actually, do you know what? Canyon Reef's leaked twice and that's because some idiot did it. And it's 53 years old and shifted 250 million tonnes of hard carbon dioxide in that time. So, you know, it's a message we need to get out there. And yeah, I will end it on that one, but those are my biggest challenges, not the technical ones. The technical ones we can solve. These are the harder ones. Thank you.
Thank you, James. So we'll have questions to the panel of three assembled speakers at the end. So next I'll invite Ben Keck from BP. And you're also representing the Northern Endurance Partnership as well today. That's right, Ben? Okay. Over to you.
Thank you. Well, good afternoon, everyone. Really nice to see everyone here. I think I've been to these events for a good few years now, and also on the advisory panel as a, I guess, representative of industry. I'm always kind of really interested in coming to these forums just because you get a very different perspective, right? It's not just all about kind of contracts, business models, and money, but there's a lot of the kind of technical aspect and the sort of next generation of people who are going to take the technology to the next level. So, as James mentioned, we had James on our project very briefly because he was the guy on Teesside who said, you know, that gathering network you're trying to build in that Teesside cluster? Well, I've walked it and I've designed it and I've walked kind of every inch of it. So I can kind of give you that blueprint and you can go build it. So I'm very pleased that at the back end of 2024, we got through to FID, to final investment decision, and to financial close. And we're in the process of actually building out the infrastructure. So what I want to kind of share with you today is really kind of quite simple. Is there's some pictures around what the construction looks like, and hopefully in that process, I can kind of talk you through going from the clusters idea that James talked about. What does it actually take for private sector, because it is still 100% private sector capital, to actually invest in the project and deliver this. So this picture is Teesside, and that picture is back when I started on the project more than 7 years ago. James mentioned 2015 Teesside Collective. I started on the project in the early stages of 2019. We still had the steelworks there. And I think one thing that James maybe forgot to mention was what's changed in 2015 to this year is in that 10 years, we potentially have got, well, we will have 7 different prime ministers. Right? So the political, to say the kind of political landscape is kind of challenging or complicated, I think is a bit of an understatement, right? It's sort of unprecedented in the UK. But really kind of kudos to the Department of Energy Security and Net Zero to be able to roll out those business models that underpins the cluster development, just because I think where industry and government are very aligned on is the idea that clusters are not just about transporting and shipping CO2, but they're really about an ecosystem. And that ecosystem comes with knowledge, with jobs, and longevity as well, which I'll touch on in a minute. So when I started, it looked like this, and for a good few years, we didn't do any construction. We did a lot of destruction. And all of that is gone now because it's more, we're building something new. But let me just make a short introduction here about NEP. So James talked about the Teesside cluster and what we proposed back in the early years was an East Coast cluster concept through our partners. We had quite a lot of partners, and eventually evolved into where we've got now, where we've got BP, Equinor, and Total Energies forming a joint venture, a standalone joint venture called the Northern Endurance Partnership Project. And what it intends to do is to deliver a kind of East Coast cluster by building out CO2 transportation and storage infrastructure to decarbonize the Teesside cluster and the Humber cluster. Why Teesside? It's the most compact cluster, so we think it's a really good testing ground, and obviously I think that was one of the first things that James worked on, so we had a blueprint. And why Humber cluster? Well, because it's as you saw in that diagram from James, the kind of tallest bars are in the Humber area, right? So we've got quite famously the Drax power plant there, very large emitter. So it makes sense that if you're going to target building out decarbonizing infrastructure, you'd go to those biggest emitters. And where NEP is today it's got phase one of the development. So that's what you see, that 145 kilometer pipeline from Teesside out to the Endurance store. And it's got a bunch of future stores as well. So we've got roughly about 6 different stores across 5 licenses. And quite recently, if you follow us on social media, we've drilled 1 additional store outside of Endurance, which has been very, very successful. It's a sort of analogous, one of those future stores that are called BC39, analogous to the Endurance store. And it's proven out to be exactly what we thought, if not better. So there's a lot of storage, and it's a world-class storage basin. Some of the kind of media numbers sometimes you hear about is something in the order of 1 billion tons. Endurance itself at its full potential can store about 450 million tons. So even if you're injecting, let's say, 10 million tons a year, which is what we're building up the Teesside pipeline, 450 million tons is 45 years worth of injection. That's a very big store. And if you project that with the additional stores, that's far, far longer as well. So there's no shortage of storage resource. And the cluster concepts and the technology works. So what's been holding us back, right? So let me talk a bit about Teesside, and then I'll talk a bit about Humber. And the defining features here, I come back to these kind of people and places. For Teesside, this is pretty iconic. It's the transporter bridge. At one point, Teesside built the steel for I think it was the Sydney Harbour Bridge. It's got a huge kind of long heritage there of heavy industry, and it was pretty iconic. Now the steelworks has been demolished, and on its site we've got the Net Zero Teesside Power Project, which is the first user that will go into the transportation and storage company, into the infrastructure. They're a separate company to NEP because NEP is a regulated company, and its sole purpose is to take CO2 from users, without any particular preference, and kind of store it for perpetuity. So in the bottom diagram there, you'll see the power plant. So that's Zero Teesside Power Plant. That's a world first CCGT power plant with a carbon capture, and it will be a flex gen. So kind of, I would say, kind of a bit of a technology stretch. First of its type. On an H-class CCGT as well, one of the kind of largest. And parts of it has started arriving on Teesside. For NEP, which I represent, what we are building out is, you can see a gathering network, the yellow line at the bottom, a gathering network to bring a few other additional emitters which we can expand, a compression station which is within the vicinity of that Net Zero Teesside Power project, HP compression that you can see there, and then the export pipelines that will go all the way out to the Endurance facility store with subsea hardware to take the CO2 and store it in the Endurance reservoir. So the major difference between NEP and HyNet is that we are storing dense phase from day one into saline aquifers, and they're not depleted stores. And why is that important? That's important because even though BP, Equinor, and Total Energies are involved, none of this has got anything to do with oil and gas, right? These stores are not depleted stores. They're not oil and gas stores. This is a brand new venture, brand new special purpose vehicle, NEP, whose sole purpose is to decarbonize the hard to abate sectors. right? So it's a new business, and it's quite a distinction because it's got, I would argue, other than the skills part of it and the project delivery part, a lot less kind of linkages with traditional oil and gas. Now, let me start by talking a little bit about some of the names that you see in this slide. So we've got an idea, we know the technology works, we've got no shortage of stores. What do you need to actually build out that infrastructure? Well, what you need is a consortium of, you need the experience, and you need a consortium of partners, supply chain, to be mobilized in order to go build this out. Right? So specifically, building out gathering networks, building out pipelines. I think we've got the UK is blessed to have a very widespread gas distribution network. So we know we can do gas pipelines. But one challenge is we haven't built a lot of that since the majority of the construction was built out. Right? So how do you restart a supply chain to actually do stuff like that? The second thing here, so we've got a consortium there for that site, building out the compression system and the gathering network. Gathering network is a company called Costain. Sometimes you see them around building all sorts of infrastructure in the UK. And then for the onshore part for HP compression, compressors, we're using a centrifugal compressor, very, very established technology, and very, very well proven. And that's very important because then you can get the supply chain, the usual suspects for those big compressor modules to actually come together with constructors and deliver it confidently. It's going to get done, right? So Technip Energies are a world-class contractor. They build lots of processing plants all around the world, and they've brought together a consortium that includes, in our case, GE for the power plants. I think they've appointed a subsidiary there to deliver the compression system modules themselves, and they've got Balfour BT to do the actual on-site construction, whilst they do the overall engineering, procurement, construction supervision. Right, so they're able to deploy their fabrication yards and their project management expertise in order to bring the consortium together and deliver the onshore parts. We've got pipelines. I mentioned steel industry. So one of the really important things for us here was how do you make full use of local content in the UK? I'm glad that I'm pleased to say we are more than 50% local content. I think to date we've got more than £2 billion worth of contracts that's been awarded to UK or UK affiliated subcontractors. And a really big one here on Teesside was the steelworks have been demolished. There are still some entities there. One of them is Liberty Steel, and Liberty Steel were the ones who rolled all of our pipelines here, the 148 kilometers offshore, as well as the sort of 15 kilometers or so onshore. So that's direct local employment that we've been able to contribute towards. But there is a challenge there because it's the same thing as I mentioned with the gathering network. You've got a plant there that was built in the 60s. They may have built lots of kind of pipelines back then, but then there's been a long period of just not building anything. So having to restart that and make sure that we can get pipelines rolled to the right quality that will withstand, that will last 50, 60 years, like that Canyon Rig example. That's quite tough, right? Because where are all the welders? Where's all those skills when you don't have continuous jobs in some of those factories? So that's onshore. Now for offshore, we've got a big outfit as well called Saipem. They own some of the biggest pipe lay vessels in the world. And they are responsible for building out that offshore pipeline, connecting the HP compression module all the way out to the first manifold in Endurance. And what they do there is to take the steel, do kind of coatings, concrete coatings, etc., and then do pipe lay, which is very well established in the offshore oil and gas industry. So able to leverage that skill set and the supply chain to do this. We've got power and comms as well. I think it's almost 100% fully electrified subsea injection system. So a company called Alcatel does something quite special. It's a DCFO, it's a direct current fiber optic network that does power and comms to communicate with our subsea trees and injection. So they're going to do something special there as well. And then another company called Technip FMC, which is very well established in the oil and gas sector because they do what we call subsea trees, which are the structures you put on top of wells in order to kind of control the injection. And you've got these gathering networks down there as well, which are the manifolds and the flow lines. So in pictures, it sort of looks like this. Onshore, we've got the site. So in the top left-hand side, we've got the quay side. The first thing that you've got to invest in the area after you've started demolishing existing works is to build out long-term infrastructure. And what does that look like? Well, you're going to bring these big modules in, so you've got to upgrade the quay side. And if you upgrade the quay side, that's good for the future projects coming in as well. So we've invested in upgrading that quay side with trains, etc. And that means any other project coming into Teesside, any heavy industry project, may be able to take advantage of some of that material handling capability. And then on the bottom left-hand side, you see that overall site. That's a drone view of what the actual site looks like. I've got more zoom-ins, which I'll go to in a minute. But you can see in the previous picture where you've got the steelworks, everything has been leveled. But that steelworks, leveling existing steelworks comes with its own challenges as well, because with steel, you've got lots of steel slag, and as plants get upgraded, typically you bulldoze them and you build on top of them. So over time, guess what's underneath the soil? A lot of uncertainty and complexity. And then I talked about the line pipe. So Liberty Steel, you can see all the kind of steel there. And to get that pipeline out to offshore, what we needed to do was go through a triple SI site, a site of special scientific interest, because there's some sand dunes before we head out to the beach. We don't want to destroy the beach for the kite surfers and the dog walkers. So we've got to tunnel underneath it. And tunneling underneath it means you've got to use a tunnel boring machine, which is the yellow picture, and I've got more zoom-ins there. That's very similar, but much smaller scale than, for example, the Thames Tideway sewer, where you've got to have these big tunnel boring machines, or even HS2. And sometimes one of the challenges here is we want to do things as environmentally conscious as possible, but that does come with a cost, and it does come with a risk, because tunneling underneath is much more complex than just digging it up, putting the pipeline, and then filling it back in. So these are kind of choices that add to costs for infrastructure in the UK. And then if you go to the right-hand side, I talked about these big vessels laying pipelines. So you've got what we call the C10 vessel, that's a nearer shore vessel. And then you've got a much deeper draft vessel, the C1, which is one of only a handful in the world that can do this. So you can't actually simply build this whenever you want to. You've got to actually wait for your slot for this vessel to come in, which I think is coming in from Cyprus in a couple of months' time. So you've got to mobilize the international supply chain. You've got to figure out what's on the order books, and you've got to design your project around there. And then finally, there's a picture of that subsea manifold, which I've got some zoom-ins on. We're actually, as of this stage, a bit more than 25% complete. I'm pleased to say we're roughly on target. We're more like about a third complete now, a year and a half post-financial close, which is pretty good going. Now, just as a bit of a zoom in, I talked about the tunnel boring machine. So in that picture, you can see in the left-hand side, that's where our compression system is going to be. You've got to, when you're kind of trying to clear out the site, I talked about steel slag, but also you get all sorts in there. You get earthworks, you get boulders, really big boulders, where if you're trying to do piling, you can't quite go through them. So you've got to either dig them out or find some way of getting rid of them. You've got to get rid of the steel slag. And then one of the things, actually, three of the things we found were unexploded ordnance. Because guess what? For a steelworks that has been there for a long time, it was a prime World War I and World War II target, right? So there's lots of bombs around. And so we've had three unexploded ordnances that we found, which we had to safely dispose of. And a whole bunch of other stuff, right? A bunch of other nasties that we've had to deal with. So you clear everything. It looks like we're piling, we're pouring concrete, and so on. But then the next really big challenge is, which is for us in the second half, how do you ramp up the construction workforce, which is expected to go up to about 3,000 people on this site. So you've got to have site officers, accommodation, systems control of work, etc. And then where are all those skills going to come from? Because we've got the same issue in the UK. We haven't been been very good at maintaining a pipeline of infrastructure projects, one after the other. So you haven't got a skilled workforce that's kind of going around. And you might have a competing workforce as well, because Hinkley Point is obviously a huge site. And if they pay better rates, then the workers are going to go over there. But if we pay more and you get into a bit of a price war, that brings up the cost for everyone. So how do you kind of get that balance, right? So there's kind of real practical aspects here. Now, just as a zoom in on that tunnel boring area, you can see here this tunnel boring machine. It's what we're doing is we're getting a local company to do this, a company called Stockton, and like most things, these are fairly specialist equipment. So you've got to kind of get the contractor at the right time. You've got to get them the ones with the right expertise, and inevitably there will be challenges and problems. Right? We'll get as much data as we can, but sometimes you might have some problems. And so far, whilst everything is going okay, I fully expect in the execution stage we will get some problems. And if I digress slightly here, a couple of years ago there was a book written by Dr. Ben Flubia called "How Big Things Get Done." He runs a department or a consultancy called Oxford Global Mega Projects at the University of Oxford, and he talks about analysis around major projects in the world and why is it so often that something like 2/3 of them go over budget or over schedule. And a really good way to think about it is once you start construction, I talked about ramping up workforce, getting the right vessels in. If you miss the slot, you've kind of you've blown the schedule. When you piece all these things together, building a mega project, certainly in the $1 billion and above, what it's like is like opening a window. You open the window and you want to shut it as soon as you can, right? So you've got a very, very tight window that you've planned in the schedule. And what you don't want is to go beyond that, which means everyone on my project team has a mentality of management of no change. Yes, if you could just make this a little bit better or that better, but there's always unintended consequences. And all those unintended consequences, they pile up, which, not that I'm suggesting that's what happened on HS2, but I suspect is a big reason. So really big focus for us is to stick to the plan and just deal with the surprises we'll inevitably get as best as possible, but sticking to that plan, right? Because once we slip anything, there's all sorts of other consequences. And Dr. Ben Flubia made a really good point. When he looked at successful projects, which includes, I think, the Guggenheim Museum, the big difference there is they spent a huge amount of time planning, thinking about modularization, and then once they start construction, they don't stop until they get it done. And that's sort of our mindset, right? We spend quite a lot of time in the early stages doing all the designing. Now is the time to deliver, right? So no tinkering. So I talked about landfall. When we go out to offshore, unfortunately, we also have bombs, unexploded bombs offshore. So that's an example there where we found some UXOs. There's a 500-pound British bomb. And quite often what I was told is these bombs are not like German bombs, right, that are unexploded. They're quite often munitions that were shot at planes that didn't quite reach there and then they landed back. So they're actually British munitions, right, that we're having to dispose of. And you can imagine it's quite complicated trying to remove them because you need specialist vessels like the one in the picture in the top left-hand side there. And also identifying these things are really hard because in the southern North Sea, it's one of the areas with the highest kind of tidal activity. And lots of the seabed churns around and gets moved around, which means a pipeline that you install 10 years ago may not be where you think you've installed it 10 years later. And a lot of the boulders, etc., you're not really sure if they're boulders or if they're bombs. Right? So that gives you a bit of a practical challenge, right? How do you clear all of them? But at the same time, you can't clear everything because you've got lots of other pipelines in that area. And it's going to cost you a fortune if you were to remove all of those boulders. And it'll, again, blow your schedule out of the water, so to speak. So there's been some kind of clever technology to try to figure things out, which is a real threat versus not. And then you get the kind of more usual things that you see globally as we prepare the seabed for pipe lay. So you've got like backhoe dredging, you've got all sorts of vessels that jets the seabed in order to allow that pipeline to be laid. So there's kind of lots of technology. And obviously, one of the things that, one of the countries that does this really well, the backhoe dredging and the jetting, guess what? It's the Netherlands, right? because obviously they do a lot of that with dikes and so on. So this is touching upon an international supply chain. Britain can't go it alone. Where we can, we will use local content, and where others are better than us at this, we bring that in, because ultimately, if you can deliver on time and on budget with the right quality, that beats everything else. So offshore, once we lay the pipeline, what we do is we will then install the kit. The onshore part, you've got these pipelines that gets coated, but offshore, we've got to think about the more shallower areas are places where fishermen fish as well. So you've got to have concrete protection, you've got concrete weight coating, you've got to make sure that concrete weight coating can withstand impacts of anchors and all sorts of stuff like that. Then you install the subsea hardware, the manifolds, the trees, which are all actually pretty massive stuff. So you need the right vessels. And then you've got plenty of fishing as well. So I hope there are no fishermen here, but clearly what will be of interest is whether or not we are installing this equipment when I don't know, it's peak lobster fishing season, or suddenly everywhere is the most productive fishing area in the UK, right? Everywhere we're installing a pipeline. So that's one of the kind of challenges we have as well. Let me just kind of move on next. So you see the hardware, so hopefully it gives you a bit of flavor. Where's the kit? What does it look like? Where is it coming from? And then finally, in terms of the kind of drilling, there's a lot of synergies with the offshore sector. So offshore pipelines, offshore trees, drilling, they're all offshore oil and gas, right? Even though we're not producing any oil and gas, this has got nothing to do with oil and gas, but the skills is very much of kind of the offshore sector. In fact, more than 80% of the scope for NEP Phase 1 is all offshore, which means your geologists, your engineers, they're all your offshore engineers, your kind of pipeliners, they're all largely from the offshore sector. And that's, I think, a really good example of a just transition moving from a high intensity kind of fossil fuel type sector to a low carbon sector. And for the wells here, as I mentioned, we drilled the BC39 well, appraisal well recently. And that rock that you see there at the bottom right-hand side, that is where we're going to store the CO2. So in the pore space within there, right? It's not an empty tank. It's filled with saline brine, very salty brine, and it's got very good pore space, and the pore space is very well connected. Hence why we can store it in a very controlled fashion, and we've also got a very thick seal, about 1 kilometer of impermeable rock, and that's what holds the CO2 there in perpetuity. So we've got the drilling, and I talked about kind of, you've got this window for execution. So what we're trying to do is we're drilling the appraisal wells first, and because we're figuring out how can we get the drill rig to be as efficient as possible. How do we make sure that what we're encountering in those stores are as well understood as possible? Then we deploy all that learning to go into the Phase 1 development, so that hopefully we'll be punching those wells exactly as planned with minimal disturbance. So that's what kind of Phase 1 looks like, and what it takes to actually deliver this with the supply chain and so on. Let me just touch briefly around the commercials, because to make this happen, clearly you've got a supply chain, you've got all of these contractors, all of them are going to need some assurance that they're going to get paid, that they're deliverable. So how do you bring all of that together? I think that's where those business models really help. You've got credible developers, you've got a credible supply chain who have done a lot of similar things before, and that's what gives bankers the confidence to finance as well. And these are, I'm pleased to say, the first CCS projects to be a majority project financed through debt financing. Global banks, I think our first round was about 23 banks all around the world. I'm being hurried on to complete what we want to do there in Teesside. You see those building blocks, the pipelines, the compression, the drilling, the trees. What we want to do is just do the same thing on Humber, right? We know that that's where the next highest density, largest industrial sector is going to be. So from our perspective, all the learning that we're going to get is going to go into the Humber. And hopefully what we then do, exactly like what we did on Teesside, is to be able to start thinking about these like Lego blocks and just kind of build them up as predictably as possible. And we think by doing that, that's going to be a big driver towards reducing your unit costs. When we get into operations, there's a whole bunch of different problems there. but I think Jackie will be able to tell you much more about that. Thanks.
Can I invite the three speakers to take a seat at the table? And I'll now open the floor to questions, comments. Okay, and I have the roving pool. There we go. I'll do that with my
Thank you very much. Thank you very much for the speakers. That's really informative and insightful. I've got two questions for Ben. So the first question is, you talk about the pipeline size is around 28 inches. So you also talk about the huge potential for the storage. I'm wondering how the size is decided, considering that in the future, probably through the expansion you talk about, you have to build more pipelines. And is there enough space to bury all the pipelines needed to fully utilize the storage space that you talk about? So that's the first question. The second question is, for the offshore platform you showed, I'm wondering in the future, is that possible to ship the CO2 directly to the offshore platform to inject it through the wells directly? If that's possible, what's the technical challenges? Thank you very much.
Thanks, Ben. Thanks for the question. So I think what you're trying to ask about is how do we match the kind of pipeline size with the storage capacity? So as James mentioned, when the cluster was developed, what we saw was line of sight to about 10 million tons, based on the existing industries at the time, 10 million tons of CO2 that would get you to, including offsets, get you to a net zero cluster. That's where the 10 really comes from. So we designed a pipeline over capacity for 10, even though we've got initially a selection of users and a license obligation to deliver 4 million tons per annum. So phase one is only 4, but we pre-invested a pipeline for 10 because we saw back then that was the landscape of what's needed to get to net zero. The challenge we have is with whether it's high energy prices or policy changes, etc., with all the different industrial sectors, that landscape constantly shifts. So if you look at it today and you say, is 10 the right number? Well, I don't know. But I suspect they also had similar questions when they were building out gas and electricity transmission networks. So you can only go with the best information you have at the time, and hopefully from there, make a judgment as to what you think it's best. As regards to the storage capacity, we have line of sight to about, our ambition is to get to about 23 million tons per annum. That's what that storage basin is going to deliver ultimately. And we have a high level of confidence to reach to 10, because the BC39 store I mentioned earlier, that's going to kind of give us another maybe 2 or 3 million tons per annum on top of the 4 on endurance. Endurance, once we start injecting, if we get an upside, that might take a bit more. And then we're also drilling another appraisal well right now as we speak, which is called BC37. And if that's successful, we'll add another kind of couple of MTPA as well. So we've got a pretty good idea, pretty high confidence we can reach that 10. Whether or not we can get to 23, that typically takes time. And I think this is where the subsurface community is generally really good at doing this, right? Nearly every sort of oil and gas province you look at, when you go into it, over time, whether it's through technology or better management of the reservoir, a better understanding of the geology, typically you find that you grow the business out there, and we are hoping for that to be the same for this CO2 basin in the southern North Sea, right? So, and then on shipping, what we would say is we have no platforms. We are a full subsea development, so you're not going to see anything out in the sea once we start injecting. Can you bring in a vessel and inject at high pressure? Well, theoretically you can. Although I think the immediate thing that comes to my mind is, as Jacky talked about, a really important part of integrity management is managing the CO2 composition. So we absolutely want to know exactly what's going into the pipeline precisely to manage the corrosion risk. So personally, I think what we will probably do is prefer an onshore injection and going out to offshore. But obviously there's a lot of other factors like what kind of pressure is it being injected to, because we don't want to waste energy as well. So James, do you have anything to add?
To be honest, I think Ben covered it. It's doable. It's just having the infrastructure in place, and it intuitively, engineering wise, it's simpler to bring the ship to the shore, offload it, put it into the pipeline, and send it back out. Many years ago, I had a conversation with someone from the Department of Energy and Climate Change. That's how old I am. It's 2 name changes ago. When we had to explain, it's actually incredibly difficult to do it. He said it's not. It just runs up, plugs in. No, because the platform it's sitting on is going up and down all the time, and offshore operations should be avoided from a risk point of view if you can do that. So it seems sensible to bring it onshore. But yeah, there's loads of technical challenges that come with it. But yeah, it's doable.
Who was first? My question is from James. How much credibility of a shared CO2 transport network is compromised by CO2 of different profile? And secondly, which is the more realistic future, CO2 of same standard or making transport infrastructure strong enough to bear CO2 of different profiles?
There has to be a standard at which any transport system accepts CO2, just like there is for gas and oil. Natural gas in this country is governed by GSMR, the regulations that has a specific specification and it's very much down on the projects to come up with a concept. I'm a great fan of the ISO standard because it's a good body of work to understand what the limits are. But eventually it comes down to a commercial arrangement and what the shipper wants in his pipeline and how much risk he takes. That means that sometimes if you're dealing with novel emitters and capture plants that have more contaminants in, they have more of a burden to get to the standard for the pipeline. I just think that's the more sensible attitude than trying to manage clusters that have flexible flows, that one day you might find that the guy with the highly nasty stream is the only guy in the system, and you're not diluting it to the right spec. So I don't think dilution in terms of in clusters works very well. So you have to have a tight specification, and you just have to turn around and say to everyone, you have to meet that. And that's just the commercial reality of it. There are lots of challenges if you don't do it that way, and too much risk, I think, for the shippers and the transport guys to handle.
Please let it be a yes/no question.
I will do my best. Dominic Fedor, Environment Agency. Thank you for a very interesting session, Ben, Jacqueline, and James. I've had 2 questions, but I have to pick one. I will pick what happens to, let's say you have an active pipeline where you require CO2 reversal to the carbon capture plant. Under what circumstances would that CO2 reversal have to take place? What would be the need for that to happen?
I'll ask the obvious. CO2 reversal as in you send it back?
Yes, you send it back to the carbon capture plant.
Yeah, not going to happen.
Is that not a consideration whatsoever?
Pipeline systems are generally designed to go one way. So you open all sorts of risks if you try and send CO2 back to a capture plant. If you have an out-of-spec system, where I've come across that concept before, is if you have an out-of-spec capture plant that sends to the pipeline, you have a valve and you shut it. So that comes to the monitoring system to ensure that you're meeting the specification, the commercial arrangements. You can't really flow backwards and send it back for reprocessing or anything like that. It just doesn't work that way, and becomes complicated because you're then, who owns the CO2? Is it coming back backwards and forwards? It's not going to work. From an engineer's point of view, that's just a nightmare we don't want to happen.
Thank you.
So let's just thank our speakers one more time. I should also thank my colleague Ben Wettenhall from Newcastle University because it was given the speakers and it's in the range and everything. I've just done the shouting bit at the end. So great.